All right, looks like, not sure why, but our live stream seems to be being affected. I'm not sure why that is. Let's see what it looks like on YouTube somewhere else. But if you're with me and you're watching this and it's live somehow, then welcome. It's week 4 in the winter 2021 semester, and uh, we're talking about AI at George Brown, so GAME3001. And it's week 4. We're talking about pathfinding, and we'll talk about that in a second. I just want to see, because I'm having a bit of a hiccup, it looks like, on YouTube today. Isn't that wonderful? That I want to see what it looks like on YouTube Studio, if it is indeed working live right now. And live seems to have an issue. Samuel. I'm sorry, Sam. It's not me. It looks like YouTube has a problem. So YouTube, it looks like it is not happening right now. So not sure why that is, but what I'm going to do is to circumvent this. I always have the ability for me to store it locally and put it up afterwards. So that's what I'm going to do. I'm going to kind of save this video, and I'll have to put up the stream later. If it changes and if my stream comes on live, that's fantastic, but it doesn't seem that I'm able to access the video at all. The live stream, I'm not sure if live streaming is just down right now on YouTube, but it's not allowing me to see my channel's live stream at all, and I can't seem to live stream. So I'm just going to save it locally. I'm just going to go to start recording locally. I'll keep streaming. Oh wait, it looks like it might be working now. Maybe. It says upcoming. I do see an upcoming stream. And let's just try it again. Hold on a sec, guys. I think it might be, I need to finish and try this over again. All right, here we go. Welcome back. We are game 3001 in the winter 2021 semester, and it's week 4, part 1 of our broadcast. And today we're talking about pathfinding. It looks like our stream is finally working, so that is a good thing. So it should be run live now. So Samuel, if you want to try out the live stream, make it totally fun. Brandon asks, are we going to get more help today for assignment 1 in the lab? Not really. Assignment 1 is kind of something that we're moving through now. We're going to go to assignment 2. We're going to start off with pathfinding today. But Brandon, I'll try and do my best to help you if you have some questions for assignment 1, if you haven't handed that in yet. All right, so let's go into this week. Miguel says, I have too many questions. Okay. So one thing to note is basic pathfinding is what we're going to be talking about today. Lab 3 is going to be due Sunday at midnight. I've talked to Alex, and it looks like Sundays are just a better time for labs. It gives the people who have him on Fridays, some of you who have him on labs on Fridays, a chance in a couple days to get your lab in. So Sunday seems to be a better day. Also due is assignment 2, which is week 6. And one thing that, if you haven't had a chance to already, please sign up for groups of up to 2 members if you haven't done so already. So please, I'd ask that you do that. I know some of you have done it and some of you haven't. Again, you want to go to Blackboard and you want to go to where it says groups. Okay, so let's go into users and groups. For me, you would go into tools, groups, and you can see that A2 groups 1 all the way to A2 groups. I think I made 50 groups. You can see that the total enrolled members are here, 1s and 2s. And there's some people that there's still some groups that are empty for people to join. If you haven't had a chance to join a group or connect with somebody else, this assignment that I talked about last week is assignment for 2 people. All right, it's not an assignment for 1. If you choose to take it on, it doesn't mean that you'll have less assignment criteria or work to do for assignment 1, for assignment 2. So if you look at assignments, steering behaviors was due Sunday, January 31st, 2021. That was a couple of days ago. All right, so we're sitting at Tuesday. So if you haven't had a chance to submit assignment 1, you can still submit it late, I believe. Tonight at midnight, but that is, or tomorrow night at midnight, I think is the final deadline. You will be losing marks for any late submissions, just letting you know. All right, so if you haven't had a chance to do that, please submit as soon as possible. Otherwise, for Pathfinding, that is due February 21st. It seems like it's far away as we're sitting at February 2nd, but it's around the corner, guys. It's not very far at all. He said it's due on Tuesday. Awesome. If he's going to, I didn't know that he changed the date. He hadn't changed it, but it's Sunday, January 31st. If that's true, let's just change it officially. So that way we don't have an issue with this. So it says, instead of Sunday, January 31st, it says Tuesday. Let's change it officially till for tonight at midnight. So that would be Tuesday, February 2nd. Just a bit of admin so that we're good and there's no issues, no one cries, especially not me. All right, so let's go into tonight at midnight. Okay, so that would adjust everything. So if you've already submitted, you're fantastic. Otherwise, so now assignment 1 is due tonight at midnight. Don't cry. Yeah, no problem. I will adjust it. So for everyone have a chance to do it. So again, let's say that, let's just put this in as in now due. We'll say that assignments 1, why does that look so big, is due tonight at midnight. So please, if you haven't had a chance to do assignment 1, make sure you get this one done. Actually, what I'll do is this week, I'll wrap this over here, which is due, right? And I think that's a reasonable place to put it for us to look at, and I'll update the thing online. All right, so that's assignment 1, due tonight at midnight. Assignment 2, due week 6. Again, we'll make it during the end of the week, so you have a chance to get there. So where are we? We're sitting at week 4, and we'll talk more about assignment 1 and everything else. We don't have to upload assignment 1 video on YouTube, Nikolai. You need to upload it somewhere, Nikolai. Right, so it needs to be a clickable link. Please don't give me a whole video. I will not accept a video. Just letting you know. It has to be a link to something, whether it's YouTube or whether it's something like Google Drive that's clickable. No, not in the slides. It needs to be a link. You need a link to it. Please give me a link to your video, just to clarify. All right, so however, wherever you put it, whether you put it on YouTube or whether you put it on thing. From a slides perspective, Ethan, I'm only looking at 1 slide. The only slide that you need for the video is a title slide with your name on it, your image, your picture of you. Take a look at the documentation, guys. So let's pull it up. You guys are looking, if you guys are asking. It's going to eat up a little bit of our time together, but it is what it is. I want to make sure you guys are good. So let's take a look at assignments. And we will look at assignment number 1 and take a look. Okay, so this was originally Sunday, January 31st. But if you scroll down to the details, okay, so this is the mark breakdown. So notice the mark breakdown says you created a zip archive properly, 2, and you made a video to demonstrate the assignment, 8. That's where the marks are. And it tells you right here, it says under submission, remove garbage files, create a zip archive, please do not use RAR. Create a short video presentation with your favorite screen capture streaming tool. We recommend OBS, and upload it to Blackboard. Right now, we're talking about the link to Blackboard. This is actually incorrect. You must also include short PowerPoint or Google Slides. That's what we're looking at, a Google Slides. That includes a single slide to start your video, and the first and only slide of your slide deck must include a current image of you. No avatars allowed. This is displayed appropriately on the page. You must also include your full name, student ID, the course code, course name, and your assignment. Please, what I'm asking for, if you haven't done it already, don't give me the video, this should say, and upload a link to it, is what it should say. Sorry, I mentioned this last time. A link, link, and upload a link to Blackboard. All right, that's what it should say. Okay, please don't give me the thing. We take a video of the PowerPoint. Yeah, you're doing a voiceover, Sean. So what's happening is you're taking a screen cap. You're recording your screen. That's what you're doing with OBS. I don't need to record your face. I don't need to see your face. I need to see your code and your application, right? So then what you're doing is the little PowerPoint slide is a single slide, which is going to be used as a header to your video, almost like a title slide. Hello, this is me. Here's my name is Tom. Here's my student ID and so on. And I'm doing a video for assignment 1. That's the only thing you have to say. And on that slide should have an image of you, current image of you, as well as what should be included in the slides. Miguel, there's only one slide, just one slide. And the only slide that you need is this one, right? On the document, it tells you first and only slide of your slide deck must include a current image of you, no avatars, and you must also include your full name, student ID, course code, the course name, and your assignment information. That's it. No need for you to put everything else in there. Submission is more confusing than the assignment. It's too bad you feel like that. Nikolai, I think it's pretty straightforward. But anyways. All right, let's continue. What if I upload both the video and the link to the video? I only want the link. I don't want your video. It's going to be like 100 megs. I don't want 100 megs for each of you. There's like 100 of you and one of me. And if I have to go through 100 megs times 100 of you, that's a lot of downloads. Please don't do that to me. All right. Do we need to upload the PowerPoint to Blackboard? No. I just need the link to your video. So, what I'll do is for, obviously this is not clear enough for some of you. You made that clear. Thank you for the feedback. What I'm going to do is I'm going to update the details for the submission requirements for the next assignment. You'll be very clear. I'll make a bullet point list of the things that you have to submit. All right. But in the submission criteria, I'll make a separate area for the short video presentation, which is another part altogether. And it'll be very clear for you. Okay. Thank you for the feedback. But what I'm looking for, and I apologize if it was a little bit confusing for some of you. So we have to use Google Slides, not just the PPT. Nikolai, I don't need either one. I don't care which one you use, Google Slides or PowerPoint. It doesn't matter. It's just you could use an image that you painted in Photoshop. You just need one slide that's a title for your video that pops up first before you talk about anything else, right? That basically shows your face, your student number, your name, and the assignment information. That's all I'm looking for, okay? But you can't show the PowerPoint using a link. I'm not sure what you mean. I don't need a PowerPoint. I'm just looking at just the link to your video, and the PowerPoint's embedded in the video. It's just you're just talking to your PowerPoint. I don't care about the PowerPoint. Sure, Photoshop a picture, a name, your ID. Make sure you have all the details in there, and you're good to go. All right, let's move on, because this is eating up a lot of our time for questions that you could have asked me a week ago. Okay, so, and I'm sorry about that. It's a little frustrating. But here what we have is we're talking about pathfinding today, and this is, if you thought steering behaviors were tough, then you're going to see that pathfinding is maybe perhaps a little bit more challenging in some ways. So remember one thing to note when it comes to pathfinding. We're starting our lecture now on pathfinding, guys. I'll answer questions around the assignments during lab for those people who have it. But really, when we talk about pathfinding, is we have an object. Let's suppose this is our hero object or our player. Sorry, guys, I have to move on. I'm not going to talk about the assignment anymore. And let's suppose we have our target, right? So let's suppose the target's way down here somewhere. And this is our target, right? Someplace, a goal, if you will, of where we want to go to. If it's just open like this, right? How is it that I'm going to have, we can use steering behaviors to get here, right? But we saw that, doing obstacle avoidance, is a challenge, right? So imagine that I have a bunch of obstacles. So I have an obstacle like this, and I have an obstacle like this, and then I have another obstacle like this, and another obstacle like this. And there are obstacles all over the place, let's suppose, to get us to the correct path. So there's a bunch of obstacles, as an example. It's not just one. And what you want to find with pathfinding is the shortest path from here to there, right? Now, obviously, and especially if you make some kind of weird block like this, so that it blocks this way, as an example. And these are irregular sized blocks. Obviously, this is a little weird, but obviously what you want to do is make a direct beeline as much as possible for this, right? But you can't go through blocks like this. And the computer doesn't know what the blocks look like. It doesn't have a sense of the path. It doesn't have any of those kind of things, right? So what we want to do is kind of give it an algorithm to follow, right? So again, example, it's going to go forward maybe, and then it's going to hit a wall, and maybe it's going to turn this way, and then it's going to hit a wall. This is the way it was first done, and then this way, and then maybe it's going to go down here. It's going to keep on going until it doesn't hit a wall, and with the idea of the notion of where it's got to be. So a couple things to note is it needs to know, so inherent knowledge of the target location. So this is one thing it needs to know, okay? It needs to have this information. Somehow it needs to know the exact location in terms of, everything else. And imagine if you can't go bulldoze through, you can't knock down barriers or anything like that. You only can go around. So it needs to know what the target is. So it knows the X and Y coordinates or the vector location of the target. It needs to know that, right? And then it's going to try and find the shortest path. So this is the pathfinding, what normally is done. Okay, typically pathfinding finds the shortest path. Okay, can't equip the player with the drill. Sorry, not for your pathfinding assignment. Nice thoughts, though. I like your thoughts. So shortest path definitely is something that it's got to find, and it can't drill through. So there are other algorithms that are exhaustive, and that means that I want to search all over the place to find my target. Imagine if I don't have inherent knowledge of where the target is. So I don't know anything about the environment. So that's a different situation. That's not the one we're talking about for us. For us, and for the stuff that we're doing here, imagine that our target is inside on the screen and we inherently know where the target is, right? If we didn't, and if we were doing a exploration algorithm, that's different than pathfinding, right? Then we would want to search in all directions. I want to search this way, this way, this way, this way, right? That's an exhaustive search, right? For if we didn't know what the target is. But we have knowledge. We have knowledge of the target. Now you're going to say this. You should think about this in the beginning. That if I have the target, if you think about it, is it fair for the computer to know exactly where the player is? Is it fair, right? And the answer for you should be no. It's not fair, right? Because it depends on the game, but for the most part, it's not fair because somehow, without seeing the target, let's suppose, and this autonomous player is what we're talking about. Let's wipe this out and really talk about what this is. This is an AI, right? This kind of player that we're talking about, an AI player or some kind of autonomous agent is really the way to talk about this more than anything else, right? So this isn't a player, but let's call this the autonomous agent. Okay, so there's autonomous agent. So that's kind of our, we want to find our way to the target, which is usually the player or something else, okay? And the autonomous agent really, I want you to think about them not knowing anything until we give it the target's location. Once the target's location is known, then we can do a couple of things with it. And we're going to see what we can do. One thing we can do, if we know where the target is we can estimate its distance. So we can sit there and say, okay, I know that as the crow flies, I have this distance, and I can use the distance formula for this. All right, so I can say, I can use square root, the Pythagorean theorem. Also, what we call is the Euclidean distance. Okay, the Euclidean distance will give us a number. right? Whatever that is. So we know the Euclidean distance. Let's try that one more time. Let's call it distance. So the distance, this distance line is something that we can figure out by basically taking the vector and plugging it into a formula with this vector and creating a number, right? And let's suppose we're just going to assign a value. So let's suppose the distance is 30 units. I'm just making a number up, okay? 30 units. So if the distance is 30 units away, we know that the best case scenario is if we fly over the obstacles, or we drill through, like some of you have suggested, right? Then the best case scenario is the distance will be 30 to the target. Okay, and the worst case scenario, the autonomous agent is going to go the wrong way, right, and search way over here and then go down around the corners, right? Which means that suppose that the distance, the worst case scenario, the distance might be something like 100, you know, or maybe it's going to squirrel around and all the different paths, weird paths to add this up. So that's the best case scenario, 30. So we have to add that in as a potential. This is the, you know, what we want. From different places, this is another thing. Every time we move somewhere, so if we have a distance here from where we start, this is the start location, right? What about if I wander to a certain spot? Over here, it's clearly farther, right? So if you do an algorithm, and if I have a spot over here, some random spot, and again, let's color this in as this is wrong. Let's suppose we don't want to really go here. Why don't we want to go here? Because this is clearly farther than the original line. This line segment here, if I went this way, right? Every frame that I move, I know the distance, right? Because I know where the target is. I know where I am, the autonomous agent. So the distance will be something more than 30. If I know that the distance is more than 30, then this might be a bad move, right? Because I'm farther away from the target than if I just went this way, okay? The challenge is, that's not the challenge. The distance is 30, right? The challenge is when I'm starting to march, right? So let's suppose I'm marching down into a straight line path, right? Yes, that's the problem. I head here as an example. Let's suppose now I keep on going where the distance is the least distance, right? So obviously this is the path I want to take, right? And let's just color the path with a different color just to make it more apparent. We'll use red. So again, I'm kind of going this way, and then maybe I want to go towards this way. Let's suppose I do some obstacle avoidance and my target is pretty small. I get to this point, right? Because this is kind of the middle place, right? It's just up away from here. You can actually redo this line and do something like, okay, we went here, we need to turn this way, and as we go to maybe about here, we pass the obstacle, and then we want to make a beeline for this again, so we're going to go down to here. That's the place we stop. Now what? How do I know that this way is better than this way? How do I know? Well, the answer is we don't, right? So here is actually a greater distance than going straight. And so is this. This is the greater distance too. But there's going to be one number. Perhaps this one is going to be worse just because we're going potentially higher away than this one, right? So let's suppose we decide we're going to go down, not up, because, you know, just the algorithm. If we come to this point here, right, and we pass the obstacle, so we pass this obstacle, what we want to start doing is traveling back this way. So we investigate these squares. Obviously, this is a bad choice, right, if I was going to be in this square. And obviously, this is going to be further than, for example, something that looks like this. So I'm probably going to choose this way because this path is open. It's not blocked. So we have blocked. We have areas that are blocked, right? And let's make it so it's not red now. Well, actually, we'll make it red, sure. So there's areas that are blocked. That's a tile. Let's say that is blocked. We'll talk about tiles in a second. So these are blocked, right? And these areas here are open, right? Open or blocked, okay? Let's continue drawing so you can see how this can go. And you might guess what it's going to do next, but I'm going to try and from here keep going in a straight line until I hit, or towards that actually to the target, right? I'm going to go here. I'm going to do some obstacle avoidance because I don't want to hit this. So maybe I'm going to go this way a little bit and then do something like this. So that might be the shortest path. right? Now this is, it might look easy, but actually what you'd have to do is you'd have to have feelers if I was going to use steering behavior to do this, right? And I could guide my steering towards the target. I know where the target is. I can guide myself through, making a decision, turning left or turning right, based on the distance to the target. But sometimes the path is not clear like this. Okay, let's redo our drawing again. And starting from scratch, I want you to think about other scenarios. Okay, for example, here's our screen again. And I'm opening up like this to talk to you about it because you're going to have the same issue. So now we're going to draw something else. So here we have a little block that goes like this, right? And we have a block that goes like this. And we have a block that goes like this, right? And we have our starting position in here. This is our start. Okay. And now we have our end position, which is way up here, right? So now or maybe even worse down here. That might be worse. Okay, because I wanted to kind of talk about these scenarios. So here's another scenario. Here's case number 2. And here we have our target or our goal. Sometimes that's called, right? So there's our target or our goal. All right. So any way I go, if I use the shortest path, right, I have to backtrack. Any way I go. Why? Because let's figure the same thing out. When I use our line, and let's make the color again different than what it was. So let's go here and change the color to red. Sure. So if I go down, I'm going to try this way, but now we're going to see that the path is blocked. So now if I go back this way, it's more expensive. The path is more expensive than if I go straight. So I'm backtracking. And the same thing happens here. I'm backtracking, right? Because it's more expensive to go here, because if I draw a line from here to here, right, or from here to here, or from here to here, as an example, you can see that the lines, there's different lines that are longer or shorter. Now it might go here at the beginning, and it might start going up this way, but one path might be to go all the way up here. It's going to collide. It can't go anywhere. It could try different squirrely things, but more or less what it's going to do potentially is do this, right? Go over here. This is one potential path, and then make a beeline for the target. Okay. The other option is to go this way, right? So these are two paths we're talking about. Go down and then make a beeline for the target. Which path is shorter? It looks like the bottom path is shorter because I'm at the bottom and this length is okay. Okay, but let's undo these changes because this is a path. What if there is no path below, right? So what if this is completely blocked? So I have a block that's in here as well, right? So this is a block. It can't go here, right? And we have no knowledge. Remember, we have no idea about the map. We have no idea that there's a block down here. We have no idea what the best way is. So we're going to explore both paths. So now it's clearly that if I do the same check, I want to go towards the target. So the first thing I'm going to do is move towards it. Then I'm going to do both paths. I'm going to go this way, right? I'm also going to go this way. Okay, I'm going to explore both ways at the same time. I don't know what the shortest path is. Let's suppose I explore this way. Well, I'm going to hit the wall, my outer wall. I'm going to go all the way up here. It could be that I'm also going to travel in a different path. But let's suppose I'm going to go up. This is one potential path. I can go across, and then from here I can head down. All right, that's one path. The other path is obviously shorter, where I go up like this and then across. This is not exactly right, but I go up to this same point and then down. So obviously this path is the shorter path. But the point that I'm trying to make here is you don't know what the shorter path, and there needs to be an algorithm to allow you to backtrack, because what can happen is if you don't do that, I start going back here and then I try and go back. I can keep going back and forth, because I can see that back over here is a shorter path than over here. Here is longer, here is longer, here is longer, then keep going from here to here, right? But we have a bunch of tiles that are blocked. Let's mark them with a B, right? So imagine that this is blocked, right, as an example. And, I have another one. So I want to make a bunch of tiles. Let's just say, here, let's just put B. So you get what I'm saying here, right? And these are all blocked too. These are, let's suppose, block, 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 And these are all blocked everywhere we go. Blocked, 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 blocked everywhere where you went, right? So you can't go this way. This is an unwalkable, undrillable, unflyable type of environment. It's a 2D flat environment. There's no way to get to the target other than going around somehow. Okay. So why am I talking about this? Because this is the kind of situation your algorithm is going to have to figure out. How do I find the shortest path to the target? Okay. Let's talk about some solutions. So we have to give them a route. And that is the idea of pathfinding. We have to get from point A to point B. We have an inherent knowledge of the path, but we need to figure out how to get there. So it's kind of, when it comes to pathfinding itself, it's definitely located, and this should say pathfinding. I'm not sure what happened to my title. But it should be located somewhere between decision making and movement. We're making a decision to move left or right, and sometimes we can combine steering behaviors with pathfinding. For example, we might want to combine arrival and look where you're going, that whole look where you're going algorithm, with pathfinding in order for us to find a direction. One thing to note is there are two primary algorithms we're going to look at. The first one is one called Dijkstra's algorithm. And the second one, and I may not be able to get to this today, but I'll try to talk about it next week, is something called A-star pathfinding. A-star pathfinding is derived from Dijkstra. One thing to know is that they are a greedy algorithm. It's a greedy algorithm. In other words, it wants to have the shortest path every single time. Doesn't mean the best path, by the way. The shortest path. Let's go back to this scenario here. What about if there was other information on the path that gave us, and we're going to talk about this during goal-oriented behavior. Let's suppose that, here, we have not just the path, but we have other information. Let's suppose that we have some kind of pickups along this path. The outer path has a bunch of these pickups that we can grab, right, along the way. This path doesn't, right? The algorithm that we create cares about the shortest path. It doesn't care if it's the best path. The best path might be a path to get to the target plus making some pickups. That's not part of this algorithm. This algorithm is a greedy, algorithm that wants to get to this target as fast as possible. Okay. So basically what we want to do, and if you notice these little things, there's a couple of ways to do this. One way to find a path is to create path nodes. Okay, path nodes. So going back to our picture here that we have, right? Let's undo some of these things. Let's suppose that the green circles now are path nodes. All right. So I create walkable areas for my object. So example might be something like I have a path node here. Hear me out for a second. I have a path node here. I have a path node here, right? I have a path node here, here, maybe somewhere in here, and some other path nodes as well. So this is a way of doing it, right? So I could declare little path nodes, right? And I'm going to put some more path nodes all over the place. So you can see that there's some obvious places to go, right? So let's suppose we'll cut it down into little path nodes, right? And we'll put some middle path nodes in here just to keep the same structure as much as possible, right? And maybe we'll put some path node down here as well. Okay. And we can assign values to each of these path nodes. So example, if I start looking at breaking down our structure in path nodes, then if I'm traveling again, I want to travel, I'm going to use the green line now. I'm going to travel from here to there, right? Or from here to there. So immediately you can see that this line here is a shorter line than this one. So I might try to go this way first because I want to go to the shortest line first. Think about this as a connected graph. All right, cool. Now, which line is shorter? I can go this way, or this way, because those are all walkable nodes, right? They're nodes in here. Okay. What about this node? Well, this node is no good, and so is this node. This is no good because there's something in between. And we can use line of sight to determine this if we're going to use some kind of path nodes. This is definitely a way of doing it. I'm not suggesting it's the best way, but let's make it so that it's a red line means bad. You have to go around, okay? So we can't do this. This is no good because there's a, this path node here is actually blocked, right? Same thing with this path node. We can't go there because that's blocked. And we can't go there, and we can't go there, and we can't go there. We can't go to those ones. Those are undoable from here, right? From this location, from this node, all right? Same thing here. From this one, this is no good, this is no good, and this is no good. We can't go to those nodes. They're closed, right, as an example. And same thing with these ones up here. They're not accessible. There's no line of sight with this one, right? But we have a line of sight with this one. So again, can't go to these ones, but we can go to these ones in here as an example. And again, from this one, you can't go here and you can't go here, but you can go here, right? So again, we can draw a line. From this one, you can't go here and you can't go here and you can't go here, right? Those are all nodes we can't travel with, but you can, it'll force you, and same thing with this one, you get the picture, right? So let's go back to that green line again. But you can go from here to here. You can do that. You can go from here to here. These are all nodes that can be connected. And you can do this kind of thing. You can go to all these nodes because these are all nodes. And think about this as a non-directed graph, right? That's what this is, a non-directed graph, where I can connect my nodes from one node to the other to find the correct path, right, all the way until I get to the target, okay? And I could also go here, and here, and here, and here. Sorry about the red and the green, but you get the, I'm just trying to show you what all the paths look like, okay? So now inside here, you can clearly see that this line here is shorter than this one. This line is longer than this one, okay? So I'm probably gonna go here. This is the first step. Okay, so now what's longer? Is this line longer, or is this line longer, or is this line longer? I'm probably gonna go this way. This is just shortest lines. I'm just marking out my path, maybe a little bit more green than the other ones. All right. Okay, now, am I going to go this way? And am I going to go this way? Am I going to go back this way? I've already gone this way, so if I can't backtrack. I want to try and prevent backtracking as much as possible, right? So now I'm going to go this way. Okay, now what's shorter, this way or this way? This one seems shorter, right, as an example. So, and this one seemed farther, so I might try it this way. Might try it. Right? Because this is an actual shorter path than this one, right? Again, I don't even know if I can see anything right now. I can't see my target, right? As an example. So I'm going to try different paths. I can also go this way, right? And this way seems shorter, but I might try this path. So I'm going to record the path I'm going to try. Now I'm going to keep going, and maybe I'm going to go back this way. Well, if I go back this way, then it's clearly that path only has going back to the path, the node I've already visited, or a new node down there. So I'm not going to go to this node. Maybe I'm going to try going to the shortest node. Maybe this one or this one. Let's suppose that this one is actually shorter. This is possible, guys. It might take me back down to the shortest node if I only had the shortest path information from one node to the other. Let's back up. But what if I had both informations, the total distance between my node where I'm going to the next node, and the distance to the target to guide me? The distance to the target. So I have both pieces of information now, right? So maybe the target distance from each node to the target, from each node to the target. I know the distance, right? And I want to go to the shortest distance to that node, right? I know this is a mess, but hey. So obviously this node is closer to the target than this node, and it's a shorter path. I'm going to go here. Let's try this again. This node is the closest thing to the target than this node, and it's a shorter path. So I'm going to go up this way. Okay, now I have two options. This node over here or this node over here. Which one is closest and which one is the farthest path? Looks like this is the right way to go because this is a closer node than this from over here. And it's probably equates, when you add them both together, equivalent to or a little bit more expensive than this one. Now we have a problem, right? Yeah, it might be closer over here, another middle node. But let's suppose that from here, where do you go? Well, you can go down. Again, because this is closer to the target, as an example, than this one is, right? And it's got a shortest path. So you're going to go down here. I'm just telling you that the way the algorithm would see it, right? It doesn't know where to go. It has no idea. It's going to try different paths, right? So now it can't backtrack to this node. This node's closed. And this node is closer than this node, so it's probably going to try and go down this way, right? Can't go back here because This path has been tried. So now, well, it can't go here, it can't go here, it can't go here, it can't go here, it can't go here. It's going to go this way, right? Or this way, because this is also an option, right? Which one's closer? This one's closer. So it's going to go this way. And then where is it going to go now? It's going to go up this way. And it's going to keep going because these paths are traversed until it goes to this node and find its way out. And that would be one path. Then it's going to back up all the way down to this node here where it made that first decision, this one right here, and it's going to try this path. It needs to try all paths, all viable paths, and trying to find the shortest path. So this path that we just made from this one to here like this and up, that is a path, but it's not the shortest path. The shortest path is this one, right? This one up here and across that way, right? Let's wipe that out because it's getting messy. So this idea of finding the shortest path is really what this is all about, right? Okay, questions for Neil. Is there smarter algorithms or can we add more parameters? You can add as many parameters as you want. We're going to talk about more parameters in a second. Does it calculate this before moving? We definitely calculate everything before moving. So far, what we've talked about is nodes and graphs. That's a way of doing it. One thing we can also talk about when it comes to graphs is weighted graphs. So weighted graphs, the way that would work is if we were going to think about a weighted graph, if I want to go from A to B and I want to find the shortest path to C, let's just zoom in here so we can look at that path as an example. If I want to find the shortest path to C, then obviously if this path is 4 and this path is 5, the total distance from A to C, the shortest distance here, is 9, right? What about if I went this way? If I went from A to D to B to C, well, then that would be 5 plus 6 is 11 and 5. Well, that's 16. So obviously this path is the shortest path based on the weighted values that are on each path length. Sometimes we can adjust the weighted values according to terrain. For example, going back to our drawing, let's suppose again we have a drawing, but this time what we have instead, right, is we have weights for different things, right? So again, we're going to draw our, let's say our autonomous agent here. So this is the start, right? And we're going to draw our endpoint again. Again, I'm just illustrating these options. Again, at the other end of the screen, somewhere down here, which is pretty common. So this is our goal or target. All right. But this time when it comes to nodes, and let's just draw a bunch of these circles again. We'll make them green, just as before. We'll make them nodes, but we'll make them weighted. We'll create a weighted graph a little bit, which is the exercise here. So let's say, for example, I have from here to here, I have a weight. We're going to talk about this. So it's all open, right? But I don't care about it being blocked anymore like we had before. Let's just suppose that there is a couple of paths, and we're going to put some values to these nodes that we have here. And again, I'm just making these values up so that way we can have this as an exercise. I'm not even making the circles the same size. Yay. So again, we're going to draw some lines between each of these things as we experiment, right? And let's suppose that going between, these are the only paths that are available. So you can't cut a path, as an example, across a node where the path doesn't exist. Okay, so these are the paths that you can go to. You can't, let's suppose you can't, in this case, go diagonally. Or maybe the only diagonal path is going to be this one. So only like one diagonal path. And let's put some values for these things. Let's put like a value of 5 to start, right? Again, these are our paths. And we'll put in another value of 6 somewhere else. So we'll say this is 6. And let's keep going. So some other values, right? And as we define our walkable values again, over and over again, as we make these paths come out, right? Let's suppose this is 8. We want to find, again, the shortest path based on adding numbers up together, right? That we've had, put into place, from ahead of time. Now, imagine if we knew the values. If I know the distance between one node and another. All right, let's suppose I know the distances, right? And again, I'm just making these values up, okay? So I want you to help me out when it comes to this thing, and help me discern what the shortest path is going to be, in a more complex, kind of diagram, maybe than what you've been given already. All right. Let's make this 12. Okay, so 12, and make this 4 or 5. And we'll make this one weird number. Maybe this is difficult terrain, but it'll make it 11. There we go. And the final number is going to be 6. Shortest path, please. What is the shortest path? And what I'm going to do is I'm going to label the numbers as well. So this is A, and we'll go B as we're making this up here, and then C, and so on, okay, in order. So start thinking about mapping this out for yourself, right? And then we want to do this exercise in our head first, because it's good to understand what we want the algorithm to do, right? Again, I'm just looking at nodes right now in terms of the way we're moving, right? So we have all these nodes, and as we're drawing these out, and it's a little bit, easy to figure out. You can actually make your own little graph, right, to practice. But if I was going to do a, like kind of a test, and I gave you a test question like this, then what would be the node? One of the lines has no angers, edef. Okay, let's make that. Thank you for that. Let's make that number something the same, like 7, or make it 9. All right, there we go. Okay, so what's the shortest path? 2 options are equal distance. Which option would you suggest, Ethan? How do I go, and how do I make those decisions? So tell me the path we would travel to first. So this is like kind of a weighted graph, all right? So one is A, E, H, I, go. Okay, I like that. So A, E, right? So remember it's, well, how would you decide to go to E from A when 5, remember we're looking at shortest goal first. Look at this. 5 is the shortest way to go. 5 is less than 6. So chances are, what I would probably want to do, let's draw a path in red now, right, is remember the algorithm we're trying to emulate here. You can see it, but what about the computer? That's the thing, right? Both are equal distance, but I'm going to go with what the computer would do, right, based on shortest path. If we know the distance, then I would definitely go this way, right? And I wouldn't go 6, I would go 5, because this is the next closest path. I'm not going to go 8, I would go 6, because this is the closest. And now I have some decisions to make. I can go 9 back this way, 12 this way, 11 this way, or 5 this way. So obviously I'm going to go 5, and then I'm going to go 5 this way and 6 this way. Uh-oh. Remember, I don't know where the goal is. I'm just going to follow the path. So if I was going to follow just the shortest path with no knowledge of the goal, then I would go this way, right? And then I would go 4 this way, and then I would go across this way to 3, and then I would go, okay, which one's closer, 5 or 6, right? So I would go 5 back down to this one, and now I'm backtracking. So I'm in a spot where if I don't allow backtracking, then I have to come back up to here, right? And I go, well, I'm either going to go 6 or 9. So I'm going to go 6, right? Here's my 6. Oh, I'm backtracking. So where am I going to go now? 9. So this is what it's going to be. So I don't want to go there. I've explored all these paths. And now I'm in trouble because I have 11 and 12. And I also have 5, but I've gone down that road and I've gone up this road. So it's either going to be 11, which is shorter than 12, right? And now I'm going to go to 5 because that's the only way I can go. So I can't go back. And I can go either 8 or 12. I'm going to try 8 first. Uh-oh, I've gone there, backtrack. And then I'm going to go to 12 and I'm stuck. So this is not good enough to know the distance, right? Let's give it some more information. Not just the weight of the path to go, but also the distance, the total distance that we would travel in terms of our lines from here to here, right? So example, what's the distance from A to this, to the goal, right? So as the crow flies, right, if you can do backtracking, if backtracking is allowed, and if we know the closest distance, okay, let's assume that we can see it in our eye, all right? So again, going back to what we said, this is obviously closer. 5 and 6 are probably equivalent, but we want to go this way first. And then, well, 8 seems to be farther. Is it closer? Is C closer than F? No, it looks like F is closer. So I'm going to go down 6, and also the number is shorter. Right now, is 11, is this G closer than I? G looks closer, but the number here is larger. So I'm going to go down here. And now what's closer, H or the goal to the path? Well, even though this number is larger, this is closer. So we're hoping that the algorithm is going to take us this way. So this would be one possible path. And the total count is 5 plus 5 is 10, 16, and 5 is 21, and 6 is 27. So 27 total cost for going this way. If I went this way, right, this is another path, we would go back and try this way. So this way is 5 plus 6 is 11. Okay, now where am I going to go? 9 this way or 5 down this way? Well, I'm going to obviously go 5. Even though this is closer, this is weighted less. So I'm going to, maybe the total weight for this one will be lower. So it's 5 and 6 and 5. And as you said, it's the same cost going this way or going this way. So we have two possible paths based on the weights and the distances. Okay. So this is some stuff to consider when we think about using nodes. We need also to have a sense of where we're going. It's not just enough to know what the total path, the cost of the path is, but actually, we have to have other information as well. All right. So one thing to note is it's not just don't have to have a path cost. This is a path cost. We can also use different kinds of path costs. We don't have to have an integer. We can make it so that it's an actual a floating point number. And most likely for us in our pathfinding examples and our adventures in pathfinding, we're probably going to have some kind of floating point number that's going to determine the total weight or of the path from one node to the other and the total cost of for the distance. Okay, so we're going to have those kind of things. And we have some kind of numerical value between one path and the other. Sometimes we use paths like this or some kind of graph. And, as an example, we also add additional information. Like, for example, let's suppose it's not just a weighted graph, but we also in math can have directed graphs. So you can only exit this node, right? And you can only exit this node, right? And you can only exit this node here. This is an input as an example. And here you can only exit this node and you can only go this way. So you can see that you can't backtrack because there's no other input other than this one. You can't go back this way. You can't backtrack because the arrow is a directed graph towards, kind of down this way. So this one would be basically like this and maybe like this, right? So this is kind of another example of a graph. This is a weighted and directed graph, all right? A weighted and directed graph would help us actually, because if you think about this, these directions, right, that we're given, the arrows, I can go this way. I can go two ways when I'm at A, down to E or across to B. I'm going to go to B because B is weighted less. Here, I have two options. I can go across to C or down to F. I can't go back to A because there is no arrow pointing back to A. I can only direct myself down to F, right? So the directed graph basically says, okay, I'm going to go back to F. Now from F, right, every other choice points to F except for one. I only have one possible choice from F to I. I must take the F to I choice because there is no way back to this way. There's just no way. I don't have an arrow that way, right? So I go here, and then from here, I can't go back to H. I only can go to the goal. And so sometimes directed graphs can help us, kind of find a path, or they constrain our path, our travel. And it could be that there's an exit but no entrance. Once you go through a door, the door closes and you can't go back anymore, right? There's also still a path, right? So A to E, E to F is an option, E to H and E to D. Obviously, E to H is okay, and we can still find the same other path this way, right? But there's no way of backtracking. We can't fool ourselves, and we don't care about the distance to the goal anymore. All we care about is following the directions. Okay, so that's two different graphs. Another reason to use graphs, before I move on, is sometimes we use graphs to produce a probability that something will happen. Okay, so in other words, not only the distance, but we can also add in another value. If the AI isn't always going to find the best path, right, as an example, we can assign a probability as well. So sometimes that happens in when it comes to pathfinding. And the reason for this is we want to add variability to an AI. We don't want it to be predictable, because that's an issue. Let's suppose that 60% of the time, right, that it's going to choose to go this way, right? And let's suppose that only 40% of the time, remember, it's got to add up to 100%, it's going to go this way. Well, then 60% of the time, it's going to try this path first, and it's going to find the goal. Once I find the goal, I can't backtrack. So chances are it's going to go like this. I can also switch these numbers around, right? If I wanted it to go this way more often than this way, I can change the probability numbers. And by the way, the probability are going to go from a range of 0 to 1, right? Where 1 is 100% and 0 is, 0% chance, and they have to add up. So example, if I add this one and this one, right, as an example, from this node, those two numbers have to add up to 100% or 1. Okay, it can't add up to 2, right? And obviously from here, from start to A, it's got to be 1. It's 100% chance, right, as an example, that it's going to go from start to A. So you can use graphs. I'm not going to go on to this example anymore. We're going to talk about this when it comes to decision making more. But you can use graphs for not just distance, but also decision making. You can assign other parameters, other values in there than just those things as well. So again, you can see here we have a room as an example, and each of the room has a bunch of connected nodes. So this is an example of some weighted graphs, and you want to determine the weight. It could be the distance. It could be the walkable ground is easier to walk in certain places. Obviously, it's easier for my node if I'm sitting here in the middle room. Let's suppose I'm right here. It's the weight to get to, let's say, this node up here, if I was traveling in this direction, right, is obviously lower than going this way or going this way. So I'm going to travel this way. Okay. So this is kind of the way of doing it when it comes to rooms. You plot nodes within the rooms themselves and create weights. Weights could also adjust your speed. They could adjust maybe energy costs. There could be an energy cost involved in traveling across the path. There could be many reasons why you want to have these numbers in place. We just talked about directed graphs, and directed weighted graphs are yet another option for us, and it doesn't allow backtracking because of the arrow. And what it talks about here is the graph class. So we can actually go through and create a graph, and each of the graphs itself has to have a series of nodes, and this means that we're going to have a node class. So now that we've talked about graphs, we can talk about Dijkstra's algorithm. So Dijkstra was a mathematician, right? He kind of figured out a way of doing pathfinding in games, right? But not just in games for not just pathfinding for games, but shortest path for determining values. Shortest path can be used in a lot of other applications. For example, it could be used for decision making. It could be used for basically, and if you think about shortest path, I can look at I can assign values to different objects and then choose to go to the object that has the lowest value. Okay. For example, I have a decision to make. I'm looking to do some facial recognition, and the face that I'm looking at has blue eyes, and I'm looking for green eyes, and I can check to see there's a value for the value of blue eyes has a certain number, right, attached to it, and the value of green eyes has another value, some other number attached to it. I can find the shortest path. I can find comparing the weighted numbers, I can say, well, you know what? I can add up all the values of all the features that I see on a face, as an example for facial recognition, and come up with a certainty that that face is the one that I'm matching, right? As an example. And it's not just the eye color, but also the shape of the face, the cheeks, the nose position, the mouth, and so on, right? You can create the shortest path, if you will, or a number that represents the decision you're going to make, whether it's something you think is matching or not. But here you can see that there is the start and the goal node, just like we've talked about before. So the start and the goal nodes that we see here, here's the start and the goal node. You can see that it starts over here and everything is equally weighted for us to go from here to here. One thing that Dijkstra does is it wants to know all of the paths, okay, to the goal, every path, not just the shortest path. It wants to do an exhaustive search of every single path from the start to the goal. An exhaustive search. That's what I want you to think of it, right? Even though it's a greedy algorithm and it's going to say, okay, well, it's 1, 2, 3, 4, 5 is the shortest path. Doesn't matter if you go this way or this way or this way. It's 5 every single time. Well, there's lots of paths to get to the goal. Lots of options. I can go this way, this way, this way, this way, this way. 5. I can go this way, this way, this way, this way, this way. 5. I can go this way, this way. Like you can see that there's tons of paths, right? Not just one. All right. And they're all the same length. Every path here is the exact same length as every other path. If I go this way or this way, it doesn't matter because I'm starting right here. It's the exact same length. Okay. So it does something called node processing. And the way that Dijkstra works is it kind of spreads out from the place of origin and it looks at a couple of options. I have a cumulative value called cost so far that I keep track of in the algorithm. Now, most pathfinding algorithms that we use, we can use something called recursion. And you should know about recursion from your algorithms class if you're taking algorithms, or maybe you've heard of it because you've programmed before. All right. But a lot of times what we do is when we look at something like, let's say, for example, this is the current node. Let's look at this situation up here. Case 1, this case up here in the right corner, right? So here's my current node, right? And I want to look at the cost so far. So the cost so far is a variable, right? As an example. And the cost so far has 0 because I'm at the current node, right? And let's suppose because between A and B, the total cost is 1.3. So if I went to B, the cost so far is 1.3, right? And this is connection 1. And then from A to, this is a directed graph, by the way, you can see the arrows. So there's only 3 options, right? B, C, or D. We can clearly see that B, the cost is 1.3 so far, and C, the cost is 1.6, and D, the cost is 3.3. You would know the cost before you travel there. Okay, you don't have to go there to know what the cost is. So the cost so far for all these numbers is the cumulative cost that we've talked about before. And this is kind of what we were talking about with our directed graphs. Okay, let's keep going. If we expand that, so we've just moved from these 3 as an example, and we're going to add these 2 options over here, E and F. That's what's happening here. So again, 1.3, 1.6, 3.3, and I have additionally 1.3 this way. But as I move across this connection, when I make it to E, now my total cost is 2.8. When I move down over here, my total cost is 3.2, whatever that is, right? That's how you would calculate, this idea of cost so far. You add it up as you move from one to the other, which is kind of what we did with our directed graphs anywhere. We have this cost so far variable that we keep track of. And so now what we can do is if we want this idea of going from one node to the other, we also have this idea of an open list and a closed list. The closed list, right, is, again, we have 2 lists. Think about this as arrays, or it could be vectors in C++. We have an open list and a closed list. The open list, right, as an example, is the paths that are available that we can traverse. The closed list are the paths that we've already been to. So example, A, B, and C, right, are part of the closed list, right? E, F, and D are part of the open list, right? And so the only places we can go is E, F, or D, right, as an example. So we've tried those kind of things out. And the way we determine the open and closed list is where we've traveled before. So we're going to try each of these paths. We're going to try and go to B. B is now part of the closed list. And now from the B path, we can't go back to A because A is part of the closed list because we moved from A. So we have a closed list happening. Okay, cool. Well, now E and F are part of the open list. So I can go either to E or to F, but not back to A because A is part of the closed list. Also, because of the directed nature of the graph, you can see that I can't go from B to C. There is no way of going. There's no path that goes from B to C. There's no path that goes from A directly to F or A directly to E, as an example. Okay, there's not, those paths don't exist. So again, we can look and see if I want to go to the goal node. Let's suppose this is the goal node now, right? Then let's take a look at this. So again, I go cost so far, 1.3, 1.6, and this is 3.3 going down this way, going across connection 3, right? Okay, so if I try this, I can say, let's try the first path. So 1.3, it makes myself go to B. Okay, the total cost from here to E, right? I would add in an additional 1.3, and so my total cost would be something like somehow 2.8, okay? And from here to here, my total cost is 3.2, right, as an example. And from here to here, the total cost is 4.6. Again, this is a directed graph. It's not like I can go back or have other options. So connections working back from the goal is connection 7, connection 5, connection 1. Okay. And that's the final path, 1, 5, and 7. The final path is the one that I've chosen based on the total cost so far. Node processing. So there's the Dijkstra pseudocode if you wanted to do it, where you have a node, a struct, which is a node record. We have the node, the connection, and the cost so far, right? And the reason why I'm going over the algorithm a little bit with you is you have to look at this. So our start record, we have a start place to go to. We make a new node record, a new one, where we have the node, the connection, and the cost so far. We set up our node to the start node, right? That's the start, whatever that is. And when we make a connection, we have no connections. We haven't taken in a connection. The cost so far starts off at 0. So this is like initialization, right? And then what we do in the pseudocode is we have open is the pathfinding list, and we want to add in the start record. So the start record would be this first list. So this is part of the open path, the open list, right? And then we want to say closed. Open is the pathfinding list, and closed is also right now the pathfinding list. Both those two things are the same list that we're looking at. Okay. Now we check. While the length of open is greater than 0, right? Then I want to find the smallest element in the open list, whatever that is. And if it's the goal node, then terminate. Otherwise, I want to say that the connections is equal to the graph, what I'm looking at, get connections of the current node that I'm on. Get those connections. And then for every connection in connections, check to see that the end node, right, is equal to the connection to get to the node that I'm looking, get to the end node. Is there the cost estimate for the end node, whatever that is going to be? This cost estimate is the thing that's going to drive Dijkstra. And there's different ways of creating a cost estimate. We can use, as an example, the distance as a cost estimate. We can use an approximate value that we can plug in there based on the total number of connections. Right? There's lots of ways we can go through this, and you can do some algorithm improvement by changing this estimate to the node to the goal node based on for each of the connections, right? And so on. I'm not going to go through this entire algorithm, but the idea is that that's how it works. So this is what Dijkstra does. So what Dijkstra does is, again, remember I talked about it being exhaustive? So it starts here at the start node, and it checks all the nodes in here. It gets to this decision marker, which is around here, starts going in both directions, this way and this way. It goes both ways, all right? It doesn't just go in the shortest path to the goal because it doesn't know the shortest path to the goal, right? We know a few things about the goal. We know maybe the relative distance from the start node or from the current node. We know those kind of things, right? But remember, it's only going to walk in the positions that are, the total path, and it's going to try and find the goal node as well, from this way as well as this way. So notice that it's going to keep going this way and keep finding the way until it even finds a way to go back down to this way. Okay. Samuel asked, if it did a complete search, then would it find it would take a while to execute? Yes. But one thing about Dijkstra is it's going to find the shortest path because it's going to find many paths, right? And it's going to take a while to execute. Okay. Let's talk about A star really quickly, and then we'll stop. Okay, because we talked about Dijkstra. A star is very similar to Dijkstra, right? So we talked about Dijkstra being, the just one algorithm. So A star is more of a direct point-to-point pathfinding algorithm, and this is kind of our preferred pathfinding algorithm. By the way, for your assignment 2, you can use either one, Dijkstra or A star. It's up to you if you want to use either one of them. And you can use something called a heuristic, which is a technique that is used for algorithm improvement. Okay, so that's what a heuristic is. So A star algorithms might just cost they just care a cost from node to node, and not a cost so far. All right, as an example. All right, so they really don't care about the cost so far. Cost so far is something that Dijkstra does. Okay. So here's an example of how node processing is done with A star instead. Okay. So our heuristic, and the heuristic is an estimate. That's what it is, an estimate of the distance, right, to the goal node. So let's suppose our goal node is G, and we start off at A. Our heuristic says our estimate to the goal node, as the crow flies between A and G, is 4.2, right? And our cost so far is 0, right? Our estimated total cost is 4.2 at this point, right? So now it has a decision to make. I can go here, or I can go here. When I look at this node, if I go to this, the heuristic says that the cost so far is 1.3. The heuristic cost, the cost from as the crow flies between B and G, is 3.2. And when you add those two things together, the estimated total cost of traveling to this node is 4.5. And the same thing goes here. I have two paths, this one or this one. This one, the heuristic tells me that I'm 3.7 away somehow from this node. My total cost so far across my link is 1.1, right? And when I add those two together, my estimated total cost is 4.8. I know this in advance of moving. So I know that this cost is 4.8 and this cost is 4.5. So therefore, I'm going to go this way. I'm not going to go here. This is closed. Why? Because it's more expensive than to go this way. All right, now let's try it again. So now I have two paths. One that goes over here. It's a total heuristic is 2.8 as an example. And my cost so far is 2.8. Why? Because I've added 1.3 plus 1.5 is 2.8. 2.8 plus 2.8 is 5.6, right? 1.3 and 1.7 is 3 for a total cost so far, plus my heuristic on the E node, which is 1.6. 1.3 and 1.7 is 3 plus 1.6 is 4.6. This makes it more desirable for me to go to E than to go to D. So therefore, I would go this way. And then from here, obviously, there's no way back because it's a directed graph. I would only go this way. You can see that this node was never visited because I decided not even to go to this node because of this simple way of doing things. And this path, this node, even though it says we see it, we've seen it and because we temporarily peek at what the next node is going to be. I've peeked at this node, I've peeked at this node, but I've never even seen this one, right? Because we never traveled to C. We peeked at C, but we never traveled there. Okay, questions around this idea of the difference between A star and Dijkstra. Dijkstra, it doesn't have a heuristic necessarily. It has an estimate, but it doesn't add it up. The heuristic can be calculated in many ways, Ethan, and we can talk about that. One way of calculating the heuristic is line of sight, direct as the crow flies, like we said before. That is definitely a way of doing it. The other way of doing it is we can use, depending on how we're doing it, we can use Manhattan distance. And we'll talk about Manhattan distance versus Euclidean distance. Euclidean distance is the difference, kind of taking the G and subtract A and we get some kind of distance between A and G. The other way of doing it is, let's say we can't do a line of sight, then we add up the Manhattan distance. Works like we go around, the reason why it's called Manhattan distance is it goes around blocks, almost like these are all streets, and in the middle you have a building like Manhattan, right? And these are all, from one block to the other, you have to go several blocks down. Each block, you can't go across, you can only go around the block, kind of thing, right? So you have to add up, it adds up the cost so far almost like twice, right? As an example. So it says, okay, what's the total cost? 1.3, 1.7, 1.4. That's the Manhattan distance, right? As an example. Whereas the Euclidean distance is as the crow flies. All right, so let's go back here. Node E is put back in the open list because a better path to it was found. All right, so here's E as an example, and let's suppose we have another option, right? Because we only did it one way. We did it this way because we found that from A to B to E was better than from A to C to E because C was more expensive than going this way. Okay, but this is also a viable path. Let's find the next viable path. We're not changing the numbers. Notice the numbers are the same. The heuristic is 3.7, and this one is thing. But we don't know if this path is going to be shorter than this one. We just know that from here to here is better than from here to here, but we can't see forward for the entire path. We don't know if this is the shortest path. We know this is the easiest path to get through. Let's try the other way. So now we try this way. Okay, we don't do an exhaustive search, but we want to try and find the shortest path. So the second time we do it, we go, okay, cool. Let's go back to C this time. We tried B, we found a path. Let's see if C is also a path or it has no path. So C, we go here, we say, okay, fine. It's 1.1 plus 3.7 is a 4.8. Cool. Now we can go to here, right, as an example, and this shows us a total cost of 4.1, where this is the total cost is of 4.6, right? Well, let's see if that makes any sense, right? So 1.1 plus 1.5 is 2.6, right? 2.6, and then plus the total cost of the estimate, right? As an example, where the estimate is 1.6, as an example, so 2.6 plus 1.6, and then we're going to get another value. We can see that this is obviously lower, this estimate, than this one. We're going to try going down here, but guess what? We found ourselves in a situation where we can't get to G from F. That means we have to go back to here. And this is the last point we had a good path. We had two nodes, 1 and 2. We tried this one because this was cheaper, but now we're going to go across E and we're going to go to G. So there's another path we found from A to C to E to G, where E is, the heuristic is 1.6, right? The cost so far is 2.6, and the connection from C to E, that's the connection from C to E. The total estimated cost is 4.2 as opposed to 4.1, but this is not a viable path because we can't get to the goal from here, okay? And the A-star pathfinding algorithm is in your slides as well, right? So that's what it does. It just basically looks from one node to the other. Okay, one node to the other. I'm not going to go through the details of the A-star pathfinding algorithm because we're going to do it in lab. Let's think about some data structures. So we've talked about some data structures. We can do a tree representation. So again, that can help us as an example. And these data structures can help us make decisions as well as find the shortest path. So a tree is very interesting. It's very quick. As an example, one thing to do is we can see that from the top of the tree, we can go either to the left or to the right. And if we want to add up the shortest path, and if I have all the numbers filled in the tree, then we can basically go to the one that's the smallest number. So example from 2, and as an example, I want to kind of find the shortest path to a particular goal. I don't even know where the goal is, if it's on the right side or the left side, but I'm going to try the cheapest one first. So I'm going to go here first. Let's suppose the goal is this one where it says 7. So I don't know that I can get here, but I already see an 8. So I'm going to go this way. I'm going to go to 3, right? From 3, I can either go to 4 or 5. I'm going to go to 4. And from 4, I can either go to the goal, or 6, I'm going to go to the goal. So I found a path this way. Okay, now what about this way? Is there another path? I'll go all the way back to my first branching point, which is here. And now I'm going to check, okay, which way can I go? I go here. So this is a total cost of, let's say, 10. Now I can go either to 10 or 9. Okay, let's go to 9. And 9, I get there, but there's no path that goes to the goal. So we X this out. Let's go back to 8. That was our decision point. Now I can go to 10 or I can go back. Let's check 10. 10, there's no path that goes to the goal. So now I'm back over here. I've checked 4. Let's check 5. So I can check 5, but we have no path to get to the goal. So now I've gone to 4 and I can check 6. Well, from 6, there's no path to get to the goal. So I found in an exhaustive search, I can find the shortest path. I found it very quickly, but I can continue if I want to by doing an exhaustive search of a tree representation. So that's how the trees would work. So the heuristic function is a way of estimation, an estimation method, in order for us to, to kind of help the algorithm. And the heuristic algorithm that we're going to develop in lab is not going to be Dijkstra, and it's not going to be A-star. We're going to make our own. And the reason for this is because your goal is to figure out how to do A-star and and Dijkstra on your own. So I'm not going to give you all that. We're going to make something similar, but we're going to use our own thing to do altogether. Again, we've been using a couple of things. There's different heuristics. One is the Euclidean distance heuristic, which is the direct distance between 2 points. So here's the goal. Then I have my distance between the 2 points is estimated based on as the crow flies, like as we say, right? One thing to note is, as an example, if there's no line of sight, right? One thing to do is to help the heuristic distance, right? Is can I draw a line between my my node and the goal? If I can't draw a line between the node and the goal, one thing you could say is go to the next line, go to the next goal, go to the next node. All right, cool. Can I draw a line between the node and the goal? No. But how about this one? Can I draw a line? I can look ahead, peek. Can I draw a line between the node and the goal? No. How about this one? Yes. Cool. I'm going to go here. And that might be a quick way of finding the goal as well, by using line of sight. What happens is when you use the Euclidean distance, it can find funky effects. As an example, if I have an outdoor level, it might look something like this, where I find the direct line of sight, where X is the closed nodes and O is the open nodes. Closed nodes are my path for the most part. This is from my start to my goal, and I traverse all these open nodes, as an example, until I find my goal. And this is something of a pattern that might emerge, as an example. Indoor might be looking totally different, and for example, maybe the areas that are white might be some kind of barrier or whatever. And what it can do is it can try and find the distance to a particular goal node, as an example, as the crow flies. But it's going to try and adjust the heuristic on the distance. So it could work better outside than inside. So heuristic for Euclidean, great for outside compared to inside. And again, you could also look at other ways in terms of heuristics. You can look at clustering, right? So clustering is great in that you look at a particular cluster, A, and if you want to, you can find the closest distance between this cluster and the next cluster. So let's suppose my goal is in the C cluster, right? I need to find a way of leaving the door, right? Going through the door, and there's only 2 paths that lead out of the door, this one or this one. So depending on where I'm at, I'm going to try to get to one of those intermediate goals first before I can leave the room and go to the next one. And the same thing goes here. The next intermediate goal would be down here in clustering, right? So I want to try to find my way the closest path to this node, which is the closest node that leads me out the door. So every cluster would have its own node, goal node, if you will, to help you move around. So we've talked about, different kinds of A-star fill patterns. There's also other heuristics. There's one called the cluster heuristic. I'm not going to go into that. There's the Euclidean distance heuristic and also something called the null heuristic. So different kinds of heuristic have different kinds of, of advantages, if you will, and optimizations depending on the type of situation that they're in. So what the null heuristic does is it does an exhaustive search of every possible path it can find, right? Where Euclidean distance heuristic goes directly from one to the other. Sometimes null heuristic is great if you're playing a resource gathering game, where it's not just the path you walk, like I said, but resources you pick up along the way. Again, you can use, so far we've been talking about nodes, but one thing we can also use, I'm just going to skip hierarchical pathfinding for now. We can also use grids, and this is in your assignment. What we've asked you to do is create a grid system. A grid system. A grid system has advantages and disadvantages, right? The advantage of a grid system is that each tile can be intelligent, right? In some way, similar to the nodes. It can also be layered underneath, for example, a tile map. So that's why it's really great. Example, a lot of times in games, we make tile maps to fill in our textures, right? So on the background. So each of the grids, as an example, can be used to house another path, to the next node. So a good example of that is, I'm not going to talk about hierarchical pathfinding right now. Let's move on to grids. So let's say we've talked about nodes and walkable nodes, but what we're going to be talking about and exploring in class is a grid. And again, I think the best way to describe a grid before we go is to use something like Excel. All right, so let's bring up Excel. Because Excel is already got a grid system in place, it's much easier for us to describe what it would look like. And if you're not familiar with Excel, it's a spreadsheet. There's also other spreadsheets that you can use as well that are free and open source, right? For example, Google has its numbers, right? Let's go here. I'm going to make the grid size, just for our purposes, 20, a font size of 20. And I'm going to look at a grid, and I'm going to define the outer walls and all those kind of things as black areas. So let's make the grid space. Again, you can make it, these are black. Okay, and again, I encourage you to try, different things like this, because you want to represent everything inside of your, before you program, you want to represent the thing that you're programming in something that makes sense, right? So this makes sense to me. This is a grid. I don't have to make the grid. It's made for me, right? And a grid is going to have some interesting information. Each grid, the grid itself, is made up of tile nodes, right? So the tile node, this tile node, it knows about its neighbors. There's some rules you can put in place about walking to different neighbors. Here are some rules, right? Diagonal walking is okay, right? That's a rule. Let's use diagonal walking is okay. And I have a start node. We'll mark that by S, right? Let me just organize this so you can see it. Here's my start node, right? And here's my goal node. And this is organized, is made by G. And let's now draw areas. Any area that's black is unwalkable, all right? You can't walk in this area. So now we can kind of discern these areas by drawing kind of like a grid, in here. And again, I encourage you to try some of these yourself, right? Where you're going to make your own little maze, as an example of these things. And what I want to do, right, when we establish this is create cases, right? We create cases where it's not going to be easy for us to figure it out, but we're going to get into these areas, these corners, which can maybe mess us up, right? So we can try the algorithm out in these different areas, right? Don't go too crazy when you start off. Start with something like this. Don't make this whole area all open so we can see the difference if it's going to do some changes here. All right, so now we have some things we have to estimate, okay? We can estimate a line between here and here as the crow flies, right? Some kind of distance. And if we're going to use Manhattan distance, the way Manhattan distance works, so here's Manhattan, okay? For Manhattan distance from S to the goal node, I don't know why that became black. Let's make that white again. Actually, let's just take away the color altogether. No fill. If from the S to the G node, the Manhattan distance right now is, we count squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, right? Across 18, 19, 20, 21, 22, 23, 24, 25, 6, 7, 8, 9, 31. So the Manhattan distance is 31. This way and this way. It doesn't matter if you go this way and this way or this way and this way, it's the same. 31 is the Manhattan distance estimate, okay? How about as the crow flies? What do you think that is? We can't draw it here in Excel, right? But we can probably estimate that the distance between here and here is something smaller, way smaller than 31, right? If we figure out what this is, the number of squares that are from here to here, as an example, we can easily figure this out because we know how many squares are from this cell to this cell, right? And we know how many squares are from this cell to this cell. And this is kind of more like what it's like on our game world, right? So I know that from this cell to this cell here, that is the X distance. So again, we said that it's 31, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So X is equal to 17 in this case. And then down from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, which makes up 31. Y is 14. What is the distance, the Euclidean distance now? What's Euclidean? Or the Euclidean estimate from S to G? How do you figure that out? Well, we know that a squared plus b squared is equal to c squared, right? A squared plus b squared is equal to c squared, which means the square root of, a squared and b squared, that's c squared, right? So again, if we pull up our little calculator, actually we can do it here, we have a calculator. We can say that the square root, right? The square root of the power, we'll say power is bad, but let's suppose we say the power of this number to the power of 2, right? Plus the power of this number to the power of 2, right? That's the what I want to find out. And let's just make sure that the square root works. If I press enter, we know that the square root is roughly 22. We would not get 22. It'd be something else, some other value, 22. So you can see that clearly the distance between this point here and this point here is 22. It's a smaller amount than 31. Okay, so how would you then use the grids before we move on? Well, if I travel to, there's some options, right? This tile, if I can travel diagonally, I know about this tile, 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 and this tile. It knows about all of its neighbors. How many neighbors does each tile know about? 3, 6, 7, 8. I know 8 neighbors, right? 3 on this side, 3 on this side. You can say that, this one and this one, because there's total of 9 squares, not including itself. So it has knowledge of 8 of its neighbors. Top right, top left, bottom right, up, down, left, and right. All those are neighbors, okay? So then it would try and go to each of the neighbors. based on the total cost. This one would be unwalkable, so it would be an unviable neighbor to go to. If a square is unwalkable, then it would have some value that's infinite. Manhattan distance would be infinite. Euclidean distance you can put as infinite. You can't walk to that square. You would never choose that square because the distance is infinite or just not walkable, not available, right? So then I only have really these squares to deal with, these squares around this area. So now it's up to you how you want to choose, but I recommend you choose the value of one of these neighbors that has the lowest value from a Manhattan distance or a Euclidean distance perspective. So if I go here, I just walked closer one square to this. That means this square here has a total distance, Manhattan distance, of 30 units. So this is a 30, right? But from a Euclidean distance perspective, you know, again, we're talking about, instead of it's 17 over 14, it's 16 and 14, right? 14 is still a thing. As an example, there's still, you know, 14 squares that I have to go down in order for me to go across. So it's 16 and 14. And if I estimate the, you know, the distance, we just plug in a value like 16. 16, if I can type properly, which is 21.26, right? So again, depending on what you're using, you know, this is 21. How about this one? So this is down this way, but it's the same number on of squares this way. So 17 and 13, this is the exact same amount. From a Euclidean, you know, a Manhattan distance perspective, these two squares are both worth 30, right? Because this is 30 and this is 30. And let's suppose that each of the tiles walking to each other are equivalent. There's no rough terrain or anything else. They're all values of 1. And if they're all values of 1, let's just zero them out. So all we care about right now is the Manhattan distance, okay, or the Euclidean distance. So Manhattan distance, these are equivalent. How about this one? So this one, right, if I was going to move up, and again, I'm not going to spend too much time, but I want to give you an idea of how this works. So if I go from here to this one, right, and let's suppose if you want to say diagonal walking is okay, but the distance instead of a 1 is 1.5. That you could do, because that makes sense, because it's farther to walk on the diagonal than it is to walk up and down, left and right, right? There's more distance to travel from here to there, right? For now, though, let's see that all the squares, even the diagonal ones, are the same, right? So here, what would that be? Well, we're moving up 1, right? So our distance that we have to travel on the y goes to 15, right? And we're moving across this way, so the distance on the x is going to go down to 60. So from a Manhattan distance perspective, right, we're looking at 21.93, but our Euclidean distance, our Manhattan is still 31, right? Here it's something else, and we would look at those two values. Okay. So you can see that. What about this one? So if I go up, let's undo those changes. So again, we're going to say that this is 17 and 14. This is the original values. So I want to go here. I want to go up 1, which is increase this to 15, right? We're not going to change the x value. So this is going to be 17. This would be 32, right? As you can see, right? And let's go back down to 16 and 15, right? Oh, actually, sorry, 17 and 14, which is what it is. Okay, what about this one? So this one over here. So this neighbor, if I was going to go out 1, that means on the x-axis, we would increase to 18. So again, 18 and 14 is 32. So this one would also be 32, right? And in this way, you can discern a walk path. Well, how about this one over here? So this one here, I'm just going to do 17 and 14. So this would be back 1 and up 1. So this is the worst case. So this would be like 31, and that'll be 33 up here. And this would be 31 down in here, as you can see. So you can see that I have 2 paths I can possibly go to if I use this methodology, right? If I'm using Manhattan distance, then I either go to this one or this one. It doesn't know as the crow flies how far away it is, but it has a sense of what I'm doing. If I'm using Manhattan distance, I might try either path, right? So if I go here, as an example, then I'm going to see that the next path is here, here, here. I'm going to walk around this way. Okay. If I go here, and it depends, it's really random because both this one and this one have the same, they're the same value, right? I could choose either one. Okay, what about this one? This is probably going to be 29. This is probably going to be 30, right? This is probably going to be 28. I'm just giving you a sense of how this works. 27, 26, 25, 24. This is probably going to be 23, 22, right? Now we make a decision because this is probably going to be 27 again. And you can see the path because of the way this works. This is probably going to be 28. And you can see that this is 29. Okay, do you see the diagonal? Everything on the diagonal here is the same. 29, 29, 28, 28, 27, 27. This would be 27 down in here as an example. And this would be 26, kind of over here. This would be 25. Again, when you come down to this point, to 24, so you're going to go 26, 25, 24. Now I have the choice to go either this way or this way. I'm going to choose 23, 22, 21, 20, right? And this is also 21, and this is also 20, and this is also 22, right? I don't know if you see that, right? But you can see that how that works farther away and so on. So you might come to a position where, well, either these are good, which way I'm going to go. I might try either one because I've got no sense. And again, I'm just estimating here. If I was here, and if you were calculating if it's actually 21, let's see if it is. It's probably 23 from what it looks like. This is looking like what it looks like here, right? And this is probably 24 because of see the diagonals? You can see the diagonals of here, 23, as an example. And this is probably 22 as well. Okay, remember, we can also walk diagonally. Diagonally is okay. And diagonally will save us in some ways, right? Because it'll also help us make a decision between which way we want to turn. For example, this, can we go across a corner, right? We know that from 25, I can go from 25, 24, or 23, because this is access to all these three neighbors. I can't walk here, but I can certainly walk diagonally across this way. So I might choose to go just this way because 23 is less than 25, okay? And from here, as an example, I can go to 23 or 22. I'm going to walk to 22, and this is where the diagonal look is going to be a little easier as I walk towards this. I'm not going to go through this exhaustive example here, but I think you get the picture, right? I encourage you to try and fill in the graph on your own. Try and fill in the graph as well. Why is this good? This is good because it matches one-to-one with, like I said, a tile map. And if I had a maze like this is okay, or I can have mountains and some other kind of terrain that I want to go to if it's outside, right? And it'll map one-to-one with walkable and unwalkable terrain. I could also include things like diagonal walking is not okay. I can say that. Diagonal walking is not okay. So it's blocked, right? Or I can say diagonal walking is expensive, is more expensive. Whatever your your rules are to the game, that's what you have to figure out. And if it's more expensive, then what you can say is, walking, on a regular square might cost 1, and maybe walking on a diagonal square might cost 1.2, right? It can be something as small as that, or it can be something as large as 1.5 if you really want to make it expensive and undesirable, right? So it really depends on how you want to make it. Okay, so once you've done this, you've established rules to your game. And again, you can make these, all of these things as part of the path. One thing to do is you can also do a processing step, okay? So I'm here in the start location. So this is my green location. Here is my goal. Let's make this a red location. This is the red. So from the start to the goal is where I want to go, right? What we can do is we can do a processing step when I lay out the entire grid. All right, maybe I have other obstacles here as well. And I could load in all of the tiles, right, that are unwalkable. Example, all the ones that are in the corners. I can load them in, including these ones and these ones and these ones and this one and all these ones. into an unwalkable list, right? All these tiles I would have in advance, right? So if I walk them into the unwalkable list, I could check to see if an object is inside of the closed list, and immediately we can include all of the tiles that are blocked. When we do a processing step, we go through the entire grid, check if the tile is blocked, and if the tile is blocked, then what we do is we make it as part of the closed list. All right, so what is our goal today in lab? Because we want to kind of do this kind of thing, and why am I not using graphs? Graphs is good. We're going to use graphs later on in another assignment, but I want you guys to learn how to use grids for a couple reasons. Grids are great from a collision detection perspective. Remember, we can do collision detection in many different ways. One way is to say, hey, you know what? If two objects are in the same square, they're colliding. All right, very simple. Also, you know what? We can discern areas that are unwalkable. We can also make it so that we can color areas that are difficult terrain. So you can do that with grids a lot easier than you can do with nodes, right? Difficult terrain. And you can think about a grid as a series of nodes that are interconnected with that are non-directed. You don't have a directed graph in this case. You have a non-directed but weighted graph of each node as it relates to every other node. So the node is going to be smart. It's going to know about its neighbor's costs. And the costs are going to be all Manhattan distance or Euclidean distance. You'll see that there's going to be a difference between one estimate and another. You might prefer Euclidean in some cases, and you might prefer Manhattan in others. Either way, and there's also other heuristics like cluster and the null heuristic, right? Depending on which one you choose, right? As an example, one thing you want to total up is the cost so far. One thing we haven't talked about is the cost so far. The cost so far is adding all of these tiles up, right? As an example, to create the shortest number. It's going to be quite a big number from here to here, as an example. Okay. But that shortest number is what we're aiming for. All right, so we've talked about pathfinding in a number of different ways. I'm just going to go back up to the top and ask the question, are you good? Any questions that you have for now, so far? I just wanted to remind you before we end the lecture portion, because we're going to start the lab in about 10 minutes, the first lab, that, again, just to remind you, tonight at midnight, you have assignment number 1. And lab 3 is going to be due Sunday at midnight, which is going to be all around pathfinding, the first part of it. And we're going to do a couple of labs just with pathfinding alone. And assignment 2 is due week 6. We're sitting at week 4, which is 2 short weeks away. Ethan says he has a lot of questions. Questions around pathfinding or around assignment 1. We're going to start the lab in 10 minutes. Yeah. Right. So lab 1, if I'm not wrong, starts right after this. Right. So the first lab starts in 10 minutes, and the second lab starts at between 4 and 6. Okay. Okay. Anyone have any questions for the lecture portion? All right, guys, then for people who attended the lecture today, thank you so much. This lecture has been recorded. Hopefully it'll help you from an understanding perspective to start doing your pathfinding assignment and think about those. No problem, Ethan. I will see you guys during lab. I'm not going to stop the Zoom session, but I'm going to stop the YouTube session so we can end off this video and then start the one for lab 1. And we'll record lab 1 between 4 and 6 this evening. Guys, thank you so much for people who are attending the lecture. For the people who are attending labs, I'll see you later. If not, I'll see you next week. Take care, guys. Thank you so much. And good luck on your assignment number 1 tonight.